Okay, guys, we are back, and so now we want to talk about the factors that affect an enzyme, factors affecting an enzyme. Well, first of all, there's substrate concentration. An enzyme is only active if the substrate is present, and the if there isn't any substrate present, then the enzyme is only going to be active. But the more substrate that is present, the more collisions that you're going to have. So the more uh, the activity of the enzyme will actually increase because if there's more substrate molecules present to fill the active sites, the more product that we're going to get. Now, however, when an enzyme's active sites are filled almost continuously, there is no possible way that you can increase the enzyme's rate of activity. It can only do as much as it can do, as many reactions that it can actually catalyze. So the maximum rate has been reached when all those active sites are filled constantly. So again, if the active sites are all filled, the activity cannot increase. Temperature affects the rate of an enzyme's activity. As we increase temperature, of course, the rate is going to increase, but we can increase the temperature so much so, or even decrease the temperature so much so that we affect the enzyme's rate. What will end up happening is if the enzyme's temperature is either too high or the enzyme's temperature is too low. So if we're outside of the operating range, we run the risk of denaturing the protein. And what do I mean by denaturing the protein? We're actually altering its structure. Remember, if you remember from chapter that dealt with the structure of a protein, remember a three-dimensional structure. The tertiary structure of a protein is when the protein is in its active form. Okay, so we must have tertiary structure. But it says if we are outside of that operating range, we run the risk of taking this three-dimensional protein that has an active site that will bind that will bind substrate, and we end up, because the temp is too high or too low, we end up denaturing. So altering its secondary and tertiary structure. So we can end up unfolding the protein back into its linear sequence. This no longer has an active site. It can no longer bind substrate. Same thing with pH. pH, we run the risk of damaging those interactions that are very important, like hydrogen bonds and so on and so forth, ionic type bonds that can occur between those R groups. So we end up altering that as well outside the operating range of pH. If the pH is too high, if the pH is too low, again, we end up denaturing the protein. So it says we have altered the structure. We have denatured the protein. It is no longer, we've gone from a 3D state to a 1, to a primary state. Okay? So this is the linear sequence. This is primary. This is tertiary. Okay? And either the pH or the temperature could alter those interactions. Okay, let's move on. More factors affecting many enzymes require cofactors to be present, whether it's an ion, an apoenzyme, or whether it's a coenzyme, a non-protein, another non-protein molecule. But it says we can have apoenzymes. Again, the apoenzymes, these refer to metals, the inorganic ions such as iron, copper, zinc, or we could also have necessary the coenzymes, which are non-protein molecules. Some of the examples of them are NAD, a nicotinamide adenine dinucleotide, or FAD, flavinadenine dinucleotide, or NADP, nicotinamide adenine dinucleotide phosphate. It says many enzymes require these to be active. But then we could also need vitamins. Vitamins, now, we could be missing the coenzymes if we're not taking in the vitamins, because vitamins are required for the production or synthesis of the coenzymes. So factors, so we're talking about what the factors that affect an enzyme's rate of activity. And we will talk about the coenzymes later, but if you remember from I think it was the second chapter that we looked in, we told the function of these guys. We said their job is to transport hydrogen ions and electrons during these chemical reactions. Okay, so nicotinamide adenine dinucleotide and FAD, both of these first two, these will be used during cellular respiration, and then the last one listed will be used during photosynthesis. But we'll talk more about these a little later. So, two things that could also, an enzyme might need activating. Some enzymes come ready to do whatever job they're supposed to do, but other enzymes may require activation. So if an enzyme needs activating, many times that activation comes from either adding a phosphate group or removing a phosphate group in order to make that enzyme active. If you remember when we talked about the endoplasmic reticulum, we said there's some enzymes present even in that lumen whose job is to activate an enzyme or to help that enzyme fold into its three-dimensional structure or whatever. And that's also done by either adding a phosphate group or removing a phosphate group or adding a carbohydrate group. Also, there could be enzyme inhibition, and usually enzyme inhibition for what I want to talk about is having product present or a field active site. Okay, product still in the active site, has not been released yet. So as that product moves away, then the enzyme will continue to do its job. Okay, and then going on a little further, we want to talk about how enzymes work in teams. Enzymes are involved in what we call enzymatic pathways or metabolic pathways. So where one enzyme performs a particular job, then the next enzyme takes the product from that reaction and it does the next job. So enzymes are involved in what we call metabolic pathways. So this is a set of enzymatically controlled steps that result in the completion of a particular product. So a metabolic pathway, for example, later we're going to talk about cellular respiration. That is a metabolic pathway that results in the completion of a product. Where we take glucose, for example, and we break it all the way down to carbon dioxide. Task. So, for example, just in glycolysis alone in cellular respiration takes 10 enzymes to take us from the original molecule, which is glucose, all the way down to the product of glycolysis, which is pyruvate. So in order for us to transform glucose to glucose 6-phosphate, we need an enzyme. Then to fructose 6-phosphate, we need an enzyme. And then to fructose 1,6 biphosphate, we need an enzyme. And it goes on and on and on, all the way down till we get to pyruvate. So it says each enzyme does a particular job, and the next enzyme performs the next task. So the product of one reaction always becomes the substrate for the next. The next enzyme comes and binds whatever that former product was. So from glucose to glucose 6-phosphate, that molecule has changed, so now we need an enzyme. So the product, glucose 6-phosphate, binds to the new enzyme. So that product becomes the substrate for the next, if that makes any sense. So very complicated. So in order for us to take glucose and convert it all the way down to carbon dioxide, many steps, many enzymes involved in that metabolic pathway. Next, we want to talk about oxidation and reduction, or redox reactions. Redox reactions are simply biochemical reactions that take place in living things. And basically what they are just energy transfers. Oxidation, which is one of the words, oxidation is a loss of electrons. So we know that reduction is the gain of electrons. Now, these two things always take place at the same time. Oxidation and reduction always takes place at the same time and at the same place, because as one molecule is giving up electrons, often accompanied by hydrogen ions, we know that the other part of the reaction has to be picking them up. So, just to give you an example of what I'm talking about, try to find me a spot to write on. Okay, so I reminded you that in living things, they are often accompanied by these hydrogen ions. So that's what we're going to be following around. So if we were to take glucose, which is C6H12O6, it's fueled by oxygen gas. So we're looking at cellular respiration. Cellular respiration. Okay, it says, remember we said as one part of the reaction is losing, the other part has to be gaining. So let's look at what happens to carbon dioxide. Carbon dioxide becomes glucose. Glucose becomes carbon dioxide on the opposite side of the reaction. Why? Because glucose is being oxidized. So it's losing electrons, and it's being accompanied by those hydrogen ions. It's being oxidized. Remember we said oxidation and reduction take place at the same time. So it says oxygen, therefore, is going to be reduced because it's going to pick up hydrogen ions being lost from the glucose. So oxygen becomes water on the opposite side. So oxidized glucose is being oxidized while oxygen gas is being reduced. So oxidation and reduction take place at the same time. So in cellular respiration, glucose will lose hydrogen ions, as well as those electrons, and become carbon dioxide. Oxygen will gain the hydrogen ions that are being lost, and it will become water. So glucose is being what? Oxidized, while oxygen is being reduced. In photosynthesis, it says the hydrogen ions are going to be transferred from water. So water will be oxidized because we're going to lose these hydrogen ions and electrons. It's the carbon dioxide are going to pick up the hydrogen ions and it will become glucose. So basically these two reactions are kind of the opposite of each other, but there's some differences that we'll talk about later. So water is oxidized, carbon dioxide is reduced. So we need the coenzymes in order for them to keep these reactions going, because they're going to be transferring these electrons that are being lost in these hydrogen ions. Okay, so the coenzymes. All right, so it says most redox reactions, they involve the coenzymes. Nicotinamide adenine dinucleotide and flavinadenine dinucleotide, so NAD plus and FAD. These are going to be the nucleotide coenzymes that are going to be necessary for cellular respiration. And then nicotinamide adenine dinucleotide phosphate is going to be the coenzyme that is going to be necessary for photosynthesis. Okay, so we're going to talk about these a little later, especially so we want to know what they do, when we'll see them. So NAD, FAD, those belong to cellular respiration. NADP plus, that belongs to photosynthesis. That's going to be I call them the cab drivers. And the way that we're looking at them now, these are the oxidized versions of the coenzymes. Remember, they're non-protein. This is the oxidized version. When they pick up the electrons and the hydrogen ions, that's when they are the reduced versions. But these are empty pairs. They're waiting to pick up the hydrogen ions and electrons. So these are the oxidized versions. And I really want to write that on the screen. Oxidized. Oxidized. Again, when they pick up the hydrogen ions. So when, for example, when NAD plus becomes NADH, this is reduced. Okay, I ran out of space. All right, the end of this taping